Good evening, everybody. I'm back for another sort of lost lecture video. In this video, I'm going to be working through the second of three topics that we weren't able to cover this year in the first half of our Calculus BC course, our AP Calculus BC course. And again, this is, as I mentioned during class when I talked about the philosophy behind pushing it aside this year. This topic is not an AP topic, so to be fair, you didn't miss anything on the AP exam. But having said that, it's just a brilliant, interesting technique. I think that it, gives you a really positive feeling of accomplishment when you successfully execute it. And even more than that, I think it really reinforces the power of substitution. Not use substitution necessarily, but just substitution in general. And I think that's one of the things that really draws me into this lesson. Now, of course, as an AP Calculus teacher, coaches the math team, I tend to have a pretty good affinity for mathematics in general, and I do enjoy myself a good computation every once in a while. So truthfully, I can admit that this technique that you're going to see today can be often pretty cumbersome, pretty challenging, like algebraically demanding and difficult to execute. But having said that, it's a pretty powerful technique. It's one that works in situations that you might not expect even. And more than that, it's a technique that does surface in the future depending on what paths you follow. I know of numerous students who have come back to me later and mentioned seeing this technique in physics and engineering coursework that they've done later. So I think it's one that's worth investigating, worth seeing, not worth assessing on, particularly in the shadow of current world events. But having said that, I want to go through this. Like, this is kind of my reward. Our finals are finished. This is my reward to myself, that I'm going to teach this lesson that I didn't get to teach because of the format of distance learning, and I'll just put it up there. And in the future, for future years, students will be able to access it. That's great. I'll have it here, and like I said, I'll get to get my mind off of things for a little bit. Is it a little bit weird that I finish grading final exams, and the first thing that I do to knock off my to-do list is teach a calculus lesson? Maybe, but that's neither here nor there. Let's focus on the topic of the day. Whenever you're looking at this, it's the topic of whatever day you want it to be. And that topic is called trig substitution. So right off the bat, you can hear the name, and I can hear the clicking as people turn it off. Because, of course, you don't tend to, like my students, I'm speaking to my students here, you don't tend to be a group as a whole that truly loves trigonometry like I do. That might be because I had a really great honors pre-calculus teacher that just kind of like made this interesting to me, and I really, thrived on the challenge of some of those trig identities. But it could also just be because trig just seems to be something where we often kind of get caught up in. So having said that, if you're not a trig person, if you don't feel like you're a trig person, well, I think that can change. But more important than that, I think there's still value here, and I think this is still interesting. This might help you see why it is that we approach some of the concepts of trigonometry, like identities. You'll see one of those places where we get to really kind of pull those rabbits out of our hats, if you will. Of course, I'm wearing a hat. So this will be a substitution technique. It will be allowing us to anti-differentiate particular types of functions, really lots of different functions, but there will be particular structures we're going to look at, and it will involve trigonometry. So in fact, if you remember the inverse trig integral work that we did, you'll be rewarded pretty handsomely. In fact, this technique I've mentioned before, this technique actually nerfs inverse trig integrals, at the cost of having to learn how to execute trig substitution. So with that said, let's go ahead and just jump in and take a look at the technique. And again, like this is more or less optional for you this year, and in the future we'll be able to teach this in the classroom, I hope, if things stick the way they are. So yeah, we'll give it a shot. So we're talking about trig substitution. Before we get to trig substitution, though, the place I want to begin is by talking about I want to talk about U substitution. So I want to talk about the traditional substitution we've done before. So I've drawn on here for us just a classic U substitution problem. How do I recognize it's a U substitution problem? Well, setting aside the fact that I wrote the problem and wrote the lesson and made the video and the template and everything else, what I want to point out is the presence of a particular structure in here. I see something, I'd call it kind of crunchy in here. I see something inside of a pretty basic function. I know how to anti-differentiate. In this case, I know how to anti-differentiate square roots of things, in general, if they're set up nicely. And I can anti-differentiate them with U substitution if a scalar multiple of the derivative of that inside happens to be a factor inside our integrand. So basically, knowing that the derivative of x squared plus 16 is 2x, literally 2x in this case, tells me that we should be able to, kind of I don't know, lasso a sort of chain rule form out of this. This must represent the chain rule of the chain rule derivative of a particular function. And that's what use substitution does. It just kind of like organizes the pieces for us and helps us see that original structure that the chain rule took the derivative of and produced this form. So here's what I mean. Again, we've done it this way. I'll stick with the technique we've used in the past. We're going to let u equal that thing that's sort of on the inside of something. Something where that, like when we do the problem, it would be whatever we decide to call u. In this case, I would hope you're comfortable with the fact that we're going to let u equal x squared plus 16. If you're thinking to yourself, well, could I just let u equal x squared? The answer is yes, but hold on to that thought for just a little bit. We will explore this just a little bit. Maybe not that exact substitution, but we'll come back to it. So keep in mind, if u is equal to x squared plus 16, in reality what we're doing is we're sort of changing the measurement system that we're using in this situation. It's kind of like in the beginning the integral was presented to us and we were measuring in inches. But now we want to measure in feet instead, which means we've got to do some conversion work. Well, in particular, if u is equal to x squared plus 16, that sort of distorts or changes the little tiny horizontal change in x into a little tiny horizontal change in u, but of course they're not one-to-one, because we know that the derivative of u, based on this relationship, is equal to 2x, times the tiny little change in x. And given that together, we can quickly create what I like to call a conversion factor, after one of my former students, Wilson Deng, who often talked about this in terms of conversions. Basically, our conversion factor, kind of like in the feet and inches situation where we'd say 1 foot over 12 inches is equal to 1. Same thing here. dx is equal to du over 2x. If you want to find the way to move from that tiny little horizontal change in x into tiny little horizontal change in u, you have to multiply by 1 over 2x. So there's what we got. This gives us, in a sense, a sort of roadmap for our substitution. Inside our integral, like let's set this up. Inside our integral, we have 2x. Then we have the square root of what we formerly called x squared plus 16. But we just defined u as being equal to x squared plus 16. So we're instead going to have 2x times the square root of u. From there, we had dx before, but we just said that we're going to convert dx using this conversion factor. So it's going to be du over 2x. Now, yeah, I'm setting the limits of integration aside, by the way. I will come right back to them. Having said that, making that little shift, you'll notice the 2x's divide out, and our integral, once we adjust it a little bit, is actually equal to the integral of the square root of du. And so in a sense, what we've just done is we've just changed our measurement system, at least a little bit. So there's kind of the start. The other thing that we need to take into account, though, is the fact that these limits of integration, although we didn't remark on it, it's pretty clear in the problem that these are x values. They're telling us to run from x equals 0 to x equals 3. So if we're switching everything to being in the u world, then we need to make sure that we're having our limits of integration as u values as well. It'd be like otherwise someone trying to measure everything and describe everything in inches, but then 3 feet to 1 foot. Like, we need to convert. We need to be consistent all the way across. Otherwise, there's an implied conversion we'd have to do anyway. So in this case, what we do is we point out that we can find those values. So it's worth reminding ourselves, if x equals 0, then u is going to be equal to 0 squared plus 16, which is equal to 16. And likewise, if x is equal to 3, again, I'm just taking these directly out of the limits of integration up here, those x values we had before, then u is going to be 3 squared plus 16, which you know is equal to 25. So given this, we now have our new limits of integration. Like, we're measuring no longer between x equals 0 and x equals 3, but u equals 16 and u equals 25. And in fact, I'm going to go ahead and throw these back here just so we don't have a linkage error. So kicking things off, that's where we are. We've rewritten this integral. Again, we've done this before. This is more conceptual than anything else. And we know how to anti-differentiate this and work from here. This is going to be equal to 2/3 u to the 3/2 power. And we're going to evaluate that from, it looks like, 16 to 25. When we do, I'll combine those two colors together. I'll factor out a GCF of 2/3 here and then apply the fundamental theorem. We're going to have 25 to the 3/2 power minus 16 to the 3/2 power. Oops. And if you're evaluating this at home or wherever it is that you're working through, this will be 125 minus 64 And that's going to be equal to 2/3 of 61, which is 122 over 3, also known as 40 2/3. So having done this, we now have our value. We know that this integral's value is 40 2/3. And I'm going to write it as a mixed number just because it's going to be a little easier for us to see later. But we found our answer. Like, we just followed the process pretty cleanly. So, okay, yeah, we did it. But the question that's probably in the back of your mind is, well, why would we devote, 5-6 minutes to working through a use substitution problem? We've already executed use substitution so many times, it's probably about second nature at this point, particularly with a really clean substitution problem like this one. Why would we go into that much depth? Well, the reality is, we are going to be doing a particular type of substitution today that's related to use substitution, but not exactly. And I find that it's really helpful to begin with the substitution we know well to sort of lead you towards this new version we're going to hit. But in fact, there is what I'd call a missing link from when I first taught this topic that I think will really help you sort of understand and see what it is that we're doing. The important thing to take away from this page, though, as we sort of reviewed use substitution, is that this integral, the definite integral from 0 to 3 of 2x times the square root of x squared plus 16 is equal to 40 2/3. So keep that in mind. What we are going to do next is we're going to basically go through this integral again, but we're not going to evaluate it. Instead, I want to point out that we could, of course, have chosen a different substitution to make. Now, we don't typically do substitution this way. We make our choice of substitution with pure and simple anti-differentiation in mind. We're trying to unlock a particular form that resembles the results of the chain rule. So we make the same sort of use substitution that mimics the sort of language and process that we use when we're differentiating via the chain rule. But we don't have to do that. We could instead perform a different substitution and get a completely equivalent integral. It may not allow us to evaluate that integral. It may not be helpful in this case, but it won't change anything about the integral except for the way it looks. So let me show you what I mean here. And I want to make sure I choose the correct one just to really take advantage of the resource I already made. So in this case, what we're going to do is we're going to make a different kind of substitution. Instead of letting u be a function of x, in other words, making a substitution and switching this into the variable u by redefining this variable u, we're going to make a completely off-the-wall substitution. Let's try this. Let's let x equal 5t plus 1. Let's, I don't know, like someone that says they're thirsty and they need a little bit of caffeine, let's shove some tea in them here. So we're going to let x equal 5t plus 1. Now, where did I get 5t plus 1? I looked on my page from doing it last year because this was the first time I really tried this. It's pretty arbitrary. But see, that's sort of the beauty of what I'm about to show you, is we think of use substitution as like a one-way street that gets us from point A to point B and then the problem's basically nerfed. That's not true. Basically, there are lots of possible substitutions. In fact, I'd say there's an infinite number of substitutions that you could choose for a given integrand. They won't all help you anti-differentiate, but that's sort of a different problem. And today we'll find that there are particular ones that look sort of bizarre, but will actually facilitate into anti-differentiation. So let's start with this. Let's just kind of play around with this game for a second and see what happens. We're going to let x equal 5t plus 1. So that's right there. Like, in a sense, we're making this change. This is how we're going to do. Well, let's think about what that changes. There's all sorts of cascading changes here. Well, if x is equal to 5t plus 1, we should be able to get an expression for dx. And looking at this expression, dx would be the derivative of 5t plus 1. That's just going to be 5 times that tiny little change in the horizontal direction, dt. And what's interesting here is if we look, this is actually ready-made for a direct substitution into our integrand, or into our integral itself. I mean, dx is 5 dt. We're just going to shove 5 dt in there. In addition, we also have that x is equal to 5t plus 1. We're going to be shoving that right in for x. Like, we're just going to replace it. Likewise, we'll do the same thing right here. We are going to literally substitute this and kind of cram it into the integral. But there's a little bit more there too. We can make all these changes, and we will in just a second, but keep in mind that there's also a change that happens here with our limits of integration. Those are, as they were before, x values. But we're switching everything into t world now, so we need to figure out what the corresponding t value would be for each of these pieces. So in looking here, if we have x equals 0, say, the t value that corresponds would have to solve the equation 0 equals 5t plus 1. I feel pretty confident that you'd be able to figure out that t is equal to -1/5. Likewise, if 3 is equal to 5t plus 1, I'm kind of doing the algebra in my head as I go here, then subtract 1, divide by 5, we'd get that the corresponding t value is 2/5. So what we've just got are new limits of integration as well. In a sense, it's like we're giving this integral a total makeover. Is that even a thing? Maybe that's copyrighted. I'm sorry. We're giving it a complete makeover and making it look very different. And we're going to see what actually happens, because this seems so arbitrary and bizarre, but something kind of neat is going to happen here. So here we go. Let's take our integral. We're going to start kind of hacking it up a little bit here. First moves I'm going to make, I'm going to replace those limits of integration with -1/5 and 2/5. So again, those are our work. Those came from us converting or finding the corresponding limits of integration to switch us into t world. Next, I want to replace that t, or that x, as we said, with our new substitution. That's going to be 5t plus 1. So of course it's going to be hard to kind of squeeze everything in here. I'm going to have to space this out. I apologize. I wanted to do a direct replacement, but we need some space. Oh, really? Sometimes this thing just isn't kind to me. There we go. So let's go right there. So we're going to substitute in for x. So in other words, as we said, we are going to put this in here. We're going to put in 5t plus 1. And then inside our integrand, or inside our radicand in our integrand, got a little bit of cand in there, we're going to substitute in 5t plus 1 as well. And of course, since x was squared, we're going to have the squared stay in too. And finally, since we have this new version of dx, we can make a substitution there as well. It says right in the work that we just did that dx is going to be equal to 5 dt. And so what we have just written here is, it's not the prettiest pony in the parade. Is that a phrase? If it's not, it should be. I really liked it. I just kind of made it up. So if we kind of rewrite this and recompose this a little bit, we've really got 10 times 5t plus 1 times the square root of 5t plus 1. I could have multiplied that out, but I don't really feel it right now. We've got this massive expression. A lot of work to transform this and just kind of make it look different, kind of for difference sake. But here's the amazing thing. The question that I would leave you with for a moment is, well, what is this integral equal to? This bizarro integral that we've just like made a random substitution into, what's its value? Let's go ask a friend. Phone a friend. I'm going to phone Desmos really fast here. So as we've mentioned before, and we've discovered on the first page with u substitution, we know this integral is equal to 40 2/3. And by the way, if we wanted to visualize that, that's the area between the x-axis and this curve, 2x square root of x squared plus 16, on the interval from 0 to 3. So it's the area of this section, of this region, that we're really representing here. You know what, I'll make this look a little bit better. There we go. So there's our region. That's what we are representing. That's 40 2/3. Well, our integral here, which it's not in the exact same form. I think the only change I need to make is put a 10 there. Let's do that. If I put this in and I add dt, the value of this integral is 40 2/3. And our region itself looks different. It's clearly not the same region, but looking at these things drawn to scale on the screen, they look pretty reasonably close to one another. Like, this looks like they have the same area, and that's because they do. All we did was change the measurement system. It's just kind of like if someone asked you how long is a yard, you could of course say 3 feet, or you could say 36 inches. Like, those things are the same. You're just measuring them in different ways. All we've done is change the way the integral looked. It hasn't changed anything else about the qualities. It's just the way it looks. We've recomposed it in a sense. So with that in mind, this is a pretty powerful thing, because what it tells us is that substitution isn't some narrow technique that only allows us to choose one, maybe two possibilities, and then use substitution does it. Substitution actually can work in other ways and still preserve the value of the definite integral, the area, if we want to think about it in a geometric way, all those things will work. And that's huge and fundamental to what we're going to attack today, which is called trig substitution. We are going to attack integrals that have a particular structure in their integrand that mimics the sort of things that we saw in inverse trig integrals. Lots of something squared and plus or minus something squared kind of things. In addition, we'll often see lots of radicals, or at least structures that resemble a radical. And what we're going to do is we're going to investigate and develop this technique that allows us to use trigonometry, and in particular a particular identity of trigonometry, to break down and recompose those integrands into the sort that we can anti-differentiate. And it's going to feel very arbitrary. It's going to feel like this, where someone's just pulling out of their hat. They're pulling out of their hat this, like, let's throw a sign in here. And it's going to feel weird, but once you get used to the structure, you're going to see that it does resolve some of the issues. It doesn't make it easy. It's not nerfing anything, but it's going to facilitate our ability to anti-differentiate. So it's a pretty powerful thing for sure. So let's talk a little bit about what it is we're going to do. And I'm going to basically illustrate the concept first, just to kind of get us in there. This is something that I like to do when I'm starting a really wild and strange technique for the first time in class. I like to just kind of like show it to you so that you kind of see where those pieces are, almost like you've pre-read about the topic. And then afterwards we develop like sort of the progression, the sequence of techniques we're going to apply, all that good stuff. So here we go. We're going to start with this definite integral. And I promise you, I'm going to demonstrate what trig substitution looks like. But before I do, I want to point out that, well, really, you don't need trig substitution for this integral. Like, here's why. It's something that might not immediately jump out at you. So take a look at this inside. Like, basically, we're talking about a particular area underneath or between the curve y equals the square root of 1 minus x squared and the x-axis on negative 1 to 1. Well, if we take this relationship and we square both sides. So again, this is me applying knowledge. Like, you might not notice this right away, although I'd hope you would. We've talked about it before, at least in AB. This would mean that y squared is equal to 1 minus x squared. If we add x squared to both sides, we get that x squared plus y squared is equal to 1. This, my friends, is a circle. So we're looking at some sort of region that has a circular structure to it. In particular, because this is only the positive version, this is basically the positive semicircle. And even more than that, we can see from that last line that this is the positive semicircle that has two key properties. It has radius length 1, because the square root of 1 is 1, and its center is the origin. So, and of course I can't write that fast, so I have to pull this all out. The center is 0, 0. So in other words, as strange as this is, that means that geometrically, what we're describing in this situation here is a particular region whose area we know how to compute. So pretend that's a semicircle because I'm decent at drawing. It's a semicircle that runs from negative 1 to 1. It's the entire positive half of the semicircle. We know how to calculate this area geometrically. That means this area is 1/2 pi times the radius squared, which is equal to pi over 2. So without doing any calculus really, I mean technically we had to interpret an integral as area, but not doing any computational calculus here, we have our area. We know the value of this definite integral. It is definitely equal to pi over 2. Well, that works nicely because it's going from negative 1 to 1. What if instead I'd asked you to do the area from, say, like here to here? Like, that region's not quite as pretty. Now, some of you that are really big on geometry could point out that there is, in fact, a way we could do this using central angles, using all sorts of interesting things. We could set up and find the areas of chord. There's lots of things you could do. Don't misunderstand me. I understand that there are ways that are out there that can do that. But to illustrate this, I want to show you the technique we're going to look at, this thing called trig substitution. So kicking it off, again, I want to point out that I'll just throw it right down here. Somewhere at the end, we need to conclude that our answer is pi over 2. So this is not truthfully a problem that you would use trig substitution on, not to get the definite integrals value, but the integral itself requires trig substitution for us to evaluate. So here's what it's going to look like, and this is going to feel really, really weird. It's going to feel strange, it's going to throw you off for a second, but there's a reason that it works. And in fact, you know what, even before I get here, let's just go back for a second and point out what the strategy is going to be with substitution, or with trig substitution here. And again, this is not something that would necessarily be intuitive at first. We're going to develop that intuition. So here's the thought. 1 minus x squared, it's not something that we can square root, right? 1 minus x squared we know is equal to 1 minus x times 1 plus x. But unfortunately, that's not equal to something squared. Like, if it was something squared, it would be in great shape, because the square root of something squared is just kind of equal to the whatever that thing was that was being squared. But unfortunately here, this isn't true. We just get the square root of two different factors, which, I don't know, leaves me kind of sad. It doesn't work the way we want it to. But here's kind of the thinking behind trig substitution. What we want is we want to make it so that 1 minus x squared is equal to a thing squared. Like, we want this situation to happen so that square rooting allows us to evaluate. Well, it doesn't necessarily work out that way, but there is a situation that we have seen before in which 1 minus something squared equals something squared. And if you have watched the trig integrals lesson, or you've run into that before, or you've just taken a pre-calculus class in the past that covered identities, we have seen this situation before. In fact, I'm going to give myself a little bit of space here, move it over, and point out that if we want 1 minus something squared to equal some other thing squared, well, I mean, we already have a circle over there too, but think about this. 1 minus sine squared is equal to cosine squared. That's just a version of the Pythagorean identity, and we've used that all the time. In fact, we used it in the previous lesson. So the truth is, this would be a great structure for us, because then that thing squared would be equal to cosine squared, or cosine of theta squared if we want to write it that way. Now, of course, you're looking at this going, but there's no sine there. Like, there's no sine, there's no cosine. Like, that doesn't make sense. But that's the thing, is if we just, finagled it a little bit, if we put a sign in there, and of course did some conversion work like we did here, we could transform this situation into one that has sines and cosines, and that therefore we could actually evaluate. That's where we're going with this technique, is we're going to make just the right choice so that we can sort of take advantage of a particular Pythagorean identity and allow us to break down the integrand just right. So let me show you what that looks like. This is all kind of wish casting for now, but I'll show you what the technique looks like. So specifically here, again, we're looking at the same structure, pointing out that, of course, geometry nerfs this problem. But having said that, we are going to make a substitution. In this case, I want to take advantage of the fact that 1 minus sine squared is equal to cosine squared. That's our motivation at this point. So I need a sine right in here, and I need it in the worst way. So I'm going to let x equal sine of theta. So far, so good. We're going to let x equal sine of theta. Well, as soon as we let x equal sine of theta, of course that means that we now have a new version of dx. So dx is going to be equal to cosine of theta times whatever the tiny little change is in theta. So we have a new conversion. Now, having said that, we also would need to deal with these limits of integration. I'm going to set them aside for a little bit. I'm just going to leave them, and we'll just use the back substitution method to finish this off. So again, this is all just kind of introductory, so bear with me here. My preference isn't to convert those guys. It's just a personal choice. So from here, we have that choice. Let's go rewrite this integral. And again, we'll take the indefinite integral version. So this is now going to be 1 minus, and we're going to replace x with sine of theta. So it's going to be 1 minus sine of theta squared. And then likewise, we're going to replace dx, I'll use it with a slightly different orange. We're going to replace dx with what is cosine of theta d theta. So there's our first move. We've got our first technique taken into place. So from here, our next move would be to rewrite this and try to simplify it a little bit. Well, we know that 1 minus sine squared is equal to cosine squared. That's literally the entire motivation of this technique. So we now have the square root of cosine squared times cosine of theta d theta. And we're going to deal with the positive values of cosine. It works out nicely if we do it this way. I know that I'm glossing over a few things here when I do. But basically, that's going to rewrite our integrand as now the square root of cosine squared, which is going to be the cosine of theta, times cosine of theta d theta. And cleaning this up, I mean, truthfully, I realized almost as soon as I finished that lesson yesterday, finished that trig integrals lesson, that truthfully, if I was going to do this, I'd probably use integration by parts. Like, I wouldn't even bother with the power-reducing identity. But whatever it is, we know how to get to and evaluate now. We have a couple different pathways to evaluate the integral of cosine squared d theta. So in a sense, what we've just done, you may not have even seen it, it was almost magic. there's no more square root. Like, we got rid of the square root. It's gone. Now we just have the integral of cosine squared. And we can evaluate that. It might not be our favorite thing, especially if we just learned trig integrals, but we have pathways to get there, whether they're integration by parts or that integral or trig identity we mentioned yesterday. So just to kind of like walk you through that step, I don't want to get caught up in this moment, like not right now, but we did talk about the fact that yesterday there is a power reducing identity, specifically the fact that cosine squared of theta is equal to 1 plus cosine of 2 theta, all divided by 2. So what I'm going to do is I'm going to make that substitution right here. I'm going to use that identity. This integrand will now be, especially if I simplify this out, it's going to be the integrand, or the integrand will be 1/2 plus 1/2 cosine of 2 theta, all of course d theta. And then from here I can anti-differentiate. In fact, I can do that really quickly. It's going to be 1/2 of theta, and then this one, if memory serves, this is going to be 1/4 the sine of 2 theta. And of course there'd be a plus c here, so I'm going to carry it around for a while, like just to be safe, but again, we will eventually be doing a definite integral, so it is what it is. So at this point you're like, yay! So successful, we did in fact just perform this thing called trig substitution. Again, I'll give you a process here in just a few minutes. The downside though is of course now our integrand, or our antiderivative, excuse me, is in terms of theta, and that's not exactly what we started with at the beginning, which is a problem. But we can still handle this because we have this new system that we're looking at. Go back to what we have right up here. So we said that x is equal to sine of theta. Well, if that's true, then theta is equal to sine inverse of x. So we can make that switch really, really quickly. So we can do exactly that. In fact, this will now be 1/2 of theta, but we just said theta is going to be sine inverse of x. Likewise, we can attack the second half here. And again, this is another one of those spots where this may be an integral that you haven't seen before, but basically there's an, I keep saying integral, I mean to say identity. There's an identity that you may not have seen before, but specifically there is the double angle identity that sine of 2 theta is equal to 2 sine of theta cosine theta. If you're curious, it comes from the fact that sine of 2 theta is sine of theta plus theta, and you can use sine, cosine, cosine, sine, and you can use one of the sum and difference identities to actually find it. That video is covered with me and a dancing darkwing duck action figure that produces a sort of scary amount of electricity. Feel free to take a look at the long way back on my channel if you want to see that. So what we'll do is we'll apply that identity here. We'll get 2 sine of theta cosine theta that goes in, and of course we'll still have plus c. Now at this point we've got a couple things to hit. You might notice of course that we have sine of theta and cosine theta and an x in here. So yeah, this isn't exactly what we were trying to get. We need to make one more move here in order to work our way through, to work our magic. Actually, I'm going to do this. I'm going to move these over just a little bit, just so that way we have some space down at the bottom. There we go. So in here we need to make a couple changes. First of all, sine of theta. We already know what sine is. Like it says right up here that x is equal to sine of theta. So we can just go ahead and write in an x. As far as cosine of theta though, we don't have an expression for cosine of theta just yet, but we can find that. If x is equal to the sine of theta, and I'm going to squeeze it in here. I know this isn't ideal, but I'm going to squeeze it in. If x is equal to the sine of theta, then that means that theta's opposite over hypotenuse gives us those two side lengths on a generic right triangle. The third side, using the Pythagorean theorem or Gogu's theorem, whatever you want to describe it as, will give us the third side square root of 1 minus x squared. And from this relationship, we can see that cosine of theta is equal to the square root of 1 minus x squared over 1. And hey, we were looking for cosine. There it is. So let's go make that substitution. Cosine, we now see, is the square root of 1 minus x squared. And we now have an antiderivative that's completely in terms of x, which is a victory. Like that's definitely something we wanted. But of course, as we mentioned at the beginning, we aren't finished. We have these limits of integration we want to hit. So if we want to evaluate this integral, we're going to need to go ahead and attack and use the fundamental theorem of calculus. So I'm basically at this point going to evaluate from x equals -1 to 1. Let's see what happens when we do. So we have 1/2 sine inverse of 1 plus it looks like 1/2 times 1 times the square root of 1 minus 1 squared. That's going to be fun. Speaking of 1, fun. Let me move this over as well. Then to subtract the second bit, we're going to subtract what happens when we get -1 in there. This will be 1/2 sine inverse of -1. Then we'll have, it looks like, plus 1/2 times -1, and then times the square root of 1 minus -1 squared. So having done all that, this looks like it's a mess. Like, I know at least one person that would just want to go like, yeah, I'm done. Like, it didn't have to simplify. Like, tempting, I know, tempting, I know. But looking in here, this actually cleans up really nice. The second term in each of these just zeroes out because 1 minus 1 squared is 0. So these both zero out. This leaves us 1/2 sine inverse of 1 minus 1/2 sine inverse of 1. Excuse me, of -1. And if we evaluate these, that's going to be 1/2. The function, or the angle whose sine is 1 for us is like 90 degrees in the range of arc sine. For us in radians, we call that pi over 2. And then on the second one, we're going to have minus 1/2 and then negative pi over 2. Like lots of trig in there for sure, but it is what it is. We've got pi over 4 minus a negative pi over 4. Well, guess what? We've got 2 pi over 4, and I hate to be that guy, but that is pi over 2, which is in fact exactly what we knew the answer had to be. So what you've just seen in gory detail is me taking my time. I am absolutely going slow here because I'm not teaching a live class. There's no bell that's going to stop me. I do have to get ready for dinner at some point, but beside the point, this works. Like, this technique is going to work. Obviously, it's a hairy adventure to get there. This is a challenge at probably every step of the way. There's so many little things that, just even here, just evaluating the trig was kind of challenging. But the important thing for us to note is that we found a way to break down this integrand that otherwise didn't facilitate anything. There wasn't a u substitution that was going to work to get us out of the square root of 1 minus x squared. There wasn't just some magical algebra that was going to take care of us. And although this particular problem was set up nicely geometrically, that's not going to be the case. Oftentimes, you'll just want to know, what is the antiderivative of the square root of 1 minus x squared? And that antiderivative is complicated. Look at that thing. Look at it. It's tough. But we have a path to get there, this thing called trig substitution. And it all comes down to making the right choice of what variable to, or which trig function to replace the variable in your problem with to break it down just right. So again, that's probably a little intense. There's a small chance I'll remove this example and put it at the end, but honestly, I like the flow of it. And since this is sort of like free of time, I think I'll probably stick with it. So having said that, our next move is to just kind of talk about the choice of substitution you're going to make. Because the truth is, it's not always going to be x equals sine of theta. There's going to be some differences in there. So on this page, I've created a sort of graphic organizer. It's not really graphic, just kind of an organized list that talks you through the sort of strategy here to choose. And the truth is, as you're looking at this, and probably somebody that's going to have to pause the video and like scribble things down, the truth is, I think these are fairly intuitive if you've already engaged with inverse trig integrals. They follow the same basic patterns we've seen before. Now I know I put a's in there. I have a squared minus u squared instead of 1 minus u squared, the structure we always worked with when we did the RFK strategy, but it's following the same pattern. If you see 1 minus u squared, you're going to use sine. Of course, the a just creates it in there. We'll show that when we get to a problem. If you have the sum of two squares, you're going to use tangent. And if you have the difference of those two squares, but with the variable first, you're going to use secant. And in here, if you're trying to figure out your progression, I've made reference to the specific version of the Pythagorean identity that we're taking advantage of. Because remember, each trig substitution is made and designed, no, I guess just made, so that you can take care of some sort of radical structure, some sort of square root that we need to break down, or just any sort of like integer over 2, like any odd integer over 2, so that we can break down the structure that we can't get out of otherwise. Now, as we're working in here, there are a couple notes to make, and obviously I can go pretty fast here because you have the ability to pause and write this down if that's what you need to do. But as far as the progression here, I want to really point out that first line. The first line, step 0 here, it says, the question asks, but which substitution do I use? And step 0 is, whoa there, bud. Whoa there. Hey, now. The important thing to note is this should not be your first strategy. This should not be the first thing you try. That you pop open a calculus practice assignment of some kind, you see an integral and you're like, ooh, trig substitution. Now, yeah, for mathemasochists like me, yeah, it's probably something that I would try to do, kind of a show-offy thing to just kind of challenge myself because I feel like I've done the other stuff already. But you got to ask yourself, is it truly necessary? You should always exhaust every other option before moving to trig substitution, because look at it. Look at that. Okay, it's beautiful because it's like all sorts of colors and stuff, but it took a long time to execute that as just kind of an introductory example. You don't want to use trig substitution unless you absolutely have to. So basically take that as your kind of warning that you want to make sure that you actually need trig substitution. If there's an easier way, use that easier way. After that, as you see in here, I'd say that this is sort of the order of frequency that they tend to show up, at least in my experience from doing this in high school, college, and teaching the class and writing some problems. Basically, sine seems to come up a lot. Same thing with tangent. They're fairly even with one another, and then secant's involved as well. So again, if you need to write this down, feel free to write it down. You have the ability to pause this video. That's wonderful. That's not something you can do in the regular classroom, so it is what it is. Now, before I move forward, though, let me pay some tribute to two little notes that I include at the bottom. The first one is that trig sub is going to work even if u substitution or inverse trig integral work could do the job as well. So trig substitution is really powerful because you're not really changing anything about the integral, you're just changing the way it looks. And oftentimes it's a really fun exercise to actually try out a problem that's really, really clean, including possibly even here, as sort of a kind of like fun aside, the problem that we started this entire assignment off with. You might just give that a shot and see what happens, and you'll see that can be pretty interesting. There are some domain issues that take place in that particular integral, but you will be able to execute your way through if you just focus on the antiderivative. In addition, for definite integrals, there are domain issues. I've made reference to them a couple times, including just a second ago. We're going to set that aside for the moment. It's not necessarily beyond the scope. It's important that we always keep that in mind, but I really want to focus on the technique, the computation here, because I think that that's where my best value to you can come from, showing you how to use trig substitution and kind of guiding you and providing you a roadmap through it. So again, I'm not going to linger here very long. Obviously, if we were in a classroom, you'd have some time to write this down, ask a few questions. I want to jump right into using and playing with this trig substitution technique. So I've got a couple of sort of like starter set, sort of warm-up-y kind of questions, and then we'll work through a short 3-question sequence that shows us trig substitution at varying levels. And you'll get a good feel for what sort of things are out there. There's obviously not going to be a test on this in 2020. There could be in the future if you're a future student watching it. But you can only ask like one really intricate trig substitution problem on an exam because you don't have a whole lot of time. So take that for what it is. Again, it's not an AP topic either at the time I'm making this video. So from here, the first place to begin, and kind of my favorite way to really quickly assess the ability of a student to use trig substitution, is to ask you just to execute the trig substitution. Just transform the integral into 1 in terms of theta. So in here, we've given you an integral, the integral of x to the 8th over the square root of 1 minus x squared, which is an integral, by the way, that could only be evaluated using trig substitution, or, just basically we'd need to use this new technique. And we want to go through and rewrite this as a trig integral. So our goal is just another integral that has theta in it. It has sines, cosines, tangents, or secants, depending on what we choose. So in here, the key element to make our choice as we work our way through is we need to decide which substitution we're going to make. And the place to look is always down inside the radical, or whatever's being raised to like the something over 2 power. So in there, I see 1 minus, I got ahead of myself. I see 1 minus x squared inside there. When I see that, and hopefully soon when you see that, I want you to think of 1 minus sine squared. So the reason 1 minus sine squared is a good idea is because we know that that's equal to cosine squared, which will allow us to sort of undo that radical structure and we'll be able to finish the problem. So with that said, what I want to do is I want to transform this so there's a sine in there. So I'm going to choose the substitution, and I'm going to let x equals sine of theta. Now, as soon as x equals sine of theta, that means dx is correspondingly cosine of theta, d theta. So we're doing that the same way as if we were doing u substitution. We're just choosing the substitution with some insider knowledge here. So when we make that switch, here's what our integrand's going to do. So we still have the integral. Up top, we have x to the 8th. Well, we just saw that x is going to be sine of theta. So we're now going to have sine of theta to the 8th power. Down below, we have the square root of 1 minus something squared? Well, that's going to be 1 minus sine of theta. Oops. Sine, here, I'll make this larger. Sine squared of theta. And then last but not least, we have dx. And dx, it says, is cosine of theta d theta. So we'll multiply in cosine of theta d theta. Now, of course, nothing's really taken flight yet. We haven't really gotten rid of anything. But remember, the whole purpose of this substitution is to get rid of the radical. We need to recompose this integrand so we can evaluate it. And 1 minus sine squared, as we've said before, 1 minus sine squared is equal to cosine squared. I can't do it. I really wanted to just do that in one swoop. I just can't do it. I feel like it would be hard to follow later if someone looked at the physical notes. So what does this do? Oops, I'll do this. So what do? We're going to make that substitution and change. So we've got 1 minus sine squared. That is going to be cosine squared. And then right here, if we have the square root of cosine squared, assuming that domain and like the signs and everything line up, we're going to now have the integral of sine of theta to the 8th over cosine of theta times cosine of theta. So in fact, let's clear this out just so we can see it. So there's where we're at. Notice now that the cosine of theta will divide out. That means that our integral now is equivalent to the integral of sine to the 8th of theta d theta. And we have just transformed that integral from a form that was sort of unlockable or unopenable, unobtainable, into a form that we can attack. Now, would this integral be fun to evaluate? Heck no. No way I want to do like a bunch of power-reducing identities on sine to the 8th, but that's not what the question asked. The question just asked us to rewrite each as a trig integral. We did that. And just making sure that I did it correctly. Let's just not get ahead of myself so I have to come back. Yep, we did it correctly. So there is kind of our first example of just executing the trig substitution. We can do one more of these though. So I've got another one down here. We got the integral of x to the 3rd over x squared plus 4 to the 5 over 2 power. Interesting problem for sure. Your eyes should, of course, be drawn to that x squared plus 4 down there. And as we mentioned before on the previous page, like this one doesn't have the 1 inside it that it did earlier. This one has x squared plus 2 squared. So if we're looking at this, we're going to actually be using, it looks like, tangent of theta. Oh, I chose the right color. Go figure. So we want to instead make a specific substitution. I want to let x, I'm sorry, I should write the word let in there. I want to let x equal 2 tangent of theta. And again, the 2 comes from the fact that we're going to try to factor out just the right GCF so we're left with a perfect Pythagorean identity. So we're going to make that switch. We're going to let x equal 2 tangent of theta. Naturally, that leads to some changes, specifically the fact that dx is equal to 2 secant squared of theta d theta. So we can now make a substitution. So digging in here, being pretty careful, we got to be really careful here. We're going to have 2 tangent of theta all to the 3rd power, and then divided by, in here, we're going to have some stuff to the 5 over 2 power. In particular, we're going to have, again, 2 tangent of theta squared, and then plus 4. And then last but not least, we know that we can replace dx. It tells us right there that dx is going to be 2 secant squared of theta d theta. So at this point, truthfully, we have changed this into a trig integral. I'd be lying if I said that's not a trig integral. We did do the trick, but we want to go just a little bit further here. So in looking at this, we want to try to transform what we can. Well, there's a couple things that I can definitely take into account here. So up top, we have 2 to the 3rd times 2, which is going to be, it looks like, 16 tangent cubed of theta times secant squared of theta. Again, that's just kind of taking care of what's in the numerator. In my denominator, I'm going to have 4 tangent squared of theta plus 4. And then, of course, this is all to the 5/2 power. If I GCF out a 4, we're going to have this over 4 to the 5/2 power. We'll deal with that. And then we'll have left over tangent squared of theta plus 1 to the 5/2. And I guess I dropped a d theta. My apologies. So from here, as far as the values that we have, 4 to the 1/2 is 2, to the 5th is 32. So this is really 16 over 32, which I hope you're okay with me rewriting as being over 2. And actually, you know what? Let's do this. Since it's over 2, let's just pull a 1/2 out in front. Why not, huh? So we still have, of course, in our numerator, we have tangent cubed of theta, secant squared of theta, d theta. Down below, tangent squared plus 1, like I think of Miss Williams, I tan by the c, but you could get there a bunch of different ways. The important thing to realize is that this is secant squared of theta to the 5/2 power. And one more time, we want to clean this up as best we can and finish this off. Well, we said there's going to be that 1/2 out in front. Got the integral of, looks like tangent cubed of theta, secant squared of theta. You can see there's just a lot of theta-ing at this point. Actually, I need a little bit more space. I'm going to move this over a little more. Then in our denominator, we've got now secant squared to the 5/2. Well, the squared and the over 2 divide out. So we've got this over secant to the 5th of theta. If we combine all this together, we'll have the 1/2 out in front. We'll have the secant squared and the secant to the 5th transforming. We'll have 1/2 the integral of tangent, that's tangent cubed of theta divided by secant cubed of theta d theta. And let's make sure one more time. Oh, that's interesting. I seem to have an extra 2 that popped out here. Why did you do that? Oh, it's a different problem. That's why. Huh. Change my own problem. Go figure. So there is our integral transformed. So again, this wasn't us evaluating. We didn't have to do the arduous labor of actually anti-differentiating and doing all that work, but we were able to transform it. And I'd say that in most years, this is sort of a multiple choice kind of version of trig substitution. It's a way for me to tell if 1, you can recognize the correct substitution, 2, if you know to evaluate and figure out that sort of residual change dx, or d theta, and include that, and 3, can you just basically use the Pythagorean identity and clean it up a little bit. So there's kind of a good starting spot. Again, this is usually the kind of the clean entry-level trig substitution approach that I take for assessment. Okay, so I think we're ready. We're going to approach this. We're going to do our first problem involving trig substitution. And I've decided I'm not going to do all 3 examples. The first one I've left at the end of the lesson is just an extra example in case you're interested. It's a fairly basic starter one, but I think this problem that we're going to do here will do a great job of illustrating the technique for us. So kicking things off here, I'm going to have a plan that I want to develop, and as usual, when we introduce a technique for the first time, I want you to sort of see the strategy and kind of have some steps as you get comfortable with it until you develop your own intuition and flow as you work through these problems. So in this case, we're going to evaluate the integral of x squared over x squared plus 1 to the 3/2 power. And if in your mind, well, to kick things off, basically, before we do anything else in this particular problem, the first step you want to follow to using trig substitution is to pause and think for a few moments. I'll write it as think and decide. The reason I say that is, as I mentioned before, do you really have to use trig substitution because your life is better if you don't? Not mine. Your life is better if you don't. So looking at this, a good thought would be to consider, what if I let u equal x squared plus 1? Would we end up with a perfect du up in the numerator? And the answer is nah. We've got an extra squared. We got an extra factor of x up there. So that does create the possibility that maybe there's some sort of integration by parts strategy that's kind of hiding in there. For sure, it's not straight u substitution, which is disappointing, but at the very least, we at least tried. We made sure that we didn't maybe have a clean, simple problem in here that we decided to dress to the nines with the most difficult technique we could find. So we got that out of the way. At least we gave it a shot. Our second move is the key substitution, or the key move of trig substitution. So it's basically to choose which trig function you're going to go with. So basically choose your sub. It's kind of like you go to Subway. Well, this is an old time. You go to Subway, you go to Togo's, go to Quiznos, and you're like, which of these am I going to order? You choose your sub. We're going to do the same thing over here. And what I mean by it, though, is we need to choose whether we're going to let x equal sine of theta, whether we're going to let it be tangent of theta, or whether we're going to let it be secant of theta. And I mean, we haven't mentioned it yet, but I mean, if you were a diehard cosine fan, you could technically do cosine and do the same basic thing as sine, but it's beside our point. So in this case, how do we decide? We've mentioned this before. We look at the sort of, I want to call it the radicand, but in reality here there's no actual radical drawn, but it's something to the 3/2 power. So we're thinking about the structure right there. I noticed that there's a plus in there, and the presence of that very plus makes me recognize that this should be x equals the tangent of theta. In addition, because we're just adding 1 or 1 squared, we're going to let our coefficient of tangent be just 1. So we're doing a substitution, a straight substitution of x equals tangent of theta, which is a really great thing. Next, of course, this is normally I used to just kind of take this for granted that would happen, but I've seen too often that it doesn't. We next need to evaluate and figure out what dx is. We need to complete our conversion here. So if x is equal to tangent, that means that dx is equal to secant squared of theta d theta. And in fact, we don't want to forget any of those pieces. We could end up using all of them as we work our way through. Our fourth move then, now that we have this, is basically we've done all the setup so far. This was us just kind of getting all the ingredients lined out on the table. Now we've got to start putting them in the pot and start mixing them together. So the next thing we're going to do is we are going to actually execute the substitution. So it's basically substitute. I'll write this as make your sub. Sounds like you've taken over the Subway franchise here. You're going to make your sub and then just kind of tidy it up a little bit. So what I mean is you've just got to clean it up so that we've got it kind of ready. We need to see what trig integral we're staring at here, and I'm going to need to evaluate. So in our particular integral here, I'm going to move all the way to the side because these do tend to take a little bit of space. We've got x squared in the numerator. I'm hoping you're okay with me saying that that's going to be equal to tangent squared of theta. Down below inside here, we've got this plus 1 to the 3 over 2 power, and that's going to be tangent squared of theta again, which we'll deal with in a moment. And then our dx is going to be replaced by secant squared of theta d theta. So there's our substitution. I guess in truth I should be doing this in red. So in fact, I'll just do this. I'll just completely cheat the system here. Boom, it's all in red. What were you talking about? Okay. So now that we have that, we've made our substitution. Everything's in place there. It's a trig integral now, but we need to clean this up so it actually has a shot at being evaluated. So moving some pieces around a little bit here. In our numerator, we do have tangent squared of theta and secant squared of theta. I'll draw our little d theta right next to that. Down below, we've said before, tangent squared plus 1, that's I tan by the c. That's going to be secant squared using one of our Pythagorean identities. So this is really secant squared to the 3 over 2. And this is another one of those little strategies that I'm using to kind of save some space and to not necessarily take up the entire page that you're working on. If we have secant squared to the 3/2 power, the 2 and the 2 divide out. That leaves us in the denominator secant cubed of theta. And if we want to clean this up just a little bit more, and I think we do, we have secant squared over secant cubed. That's going to leave us a single factor of secant in our denominator. So we'll now have tangent squared of theta over secant of theta d theta. So there it is. We've done our stuff. Like, we're in pretty good shape here. We've done some successful pieces. The question is, what do we want to do next? Because this isn't a trivial problem. In fact, you can tell I'm like sneaking a peek at my thing going, okay, I want to make sure I do the next move because I tend to sometimes do things the hard way. In truth, there are a bunch of different ways we could approach the integral from this point. And in fact, our next step, as you could probably predict, is going to be to evaluate. Like, we just need to evaluate this trig integral. And in fact, let me add that in there. That wasn't in my steps before. We want to evaluate the trig integral. So in doing this, we need to figure out like what structure we have. So, and as I've said, like you might see a different approach than I do just based on the identities that are here. But as I look at this, the one that jumps out at me the most is actually kind of a surprising one maybe for some people. I recognize or look at this integral, and what I see is, well, okay, it's got to stay an integral. That doesn't change. I still see the secant of theta in the denominator, and of course the d theta. But what I'm noticing is that we have tangent squared up top, and if you'll recall, we mentioned yesterday that tangent squared is equal to secant squared minus 1. Oops, secant squared minus 1. And the reason is, if tangent squared plus 1 is secant squared, then secant squared minus 1 is tangent squared. So I'm going to actually rewrite our numerator as secant squared of theta minus 1. It's at this point, by the way, that we are basically away from the calculus for a little bit. We're functioning purely in the world of pre-calculus and just trying to execute and find the right pathway of identities to get us through this situation. So we start there. We've got the integral of this thing. The next move I'm going to do is also not a calculus thing. It's sort of a pure algebra thing. I'm going to rewrite this as secant squared of theta and then minus 1. And I'm going to separate it so we have secant squared over secant of theta minus 1 over secant of theta. And again, I know I'm using the wrong color here. I should be using pink almost purely. In fact, I guess I can. For the purpose of the video, you saw what I needed you to. There's what we have. We now have two separate pieces, which means that our integral is now the integral of secant of theta minus cosine of theta. And to be fair, that's actually a huge victory right now. Cosine of theta, we know how to anti-differentiate cosine. And actually secant of theta we know as well. So this might not be one that's kind of on the tip of your tongue, but if you'll recall, we did state, even in the previous video, that the integral of secant of theta is equal to, and we can take it as a given from now on, the ln of the secant of theta plus the tangent of theta, all plus c. So basically we have this now as a given, and I'd like to fit it somewhere else, honestly. Where can I throw it? Like, I just kind of need to throw it somewhere here. I'll put it over here. This is a thing now. Here it'll look like in the video, I bet, that I'm thinking it with my green brain. Actual brain should not be green, but that's life. Okay, so we've got that as a given. So what are we going to do? We can actually evaluate this really quickly. So this expression, this integral we have, which I'm going to move to the side just to make sure I have enough space, this is going to be equal to the natural log of the absolute value of secant of theta plus tangent of theta. No shorthand way for that. Well, there is, but it's beside the point. And then minus sine of theta, all plus c. From hitting here, then, we've basically got everything in our trig integral, but at this point, that does leave us with one final step for us to attack. Our final move here is that we have an integrand, or we have an antiderivative in terms of theta, but our final thing needs to be in terms of x like our original integral was. Like, there's no way the derivative of ln of secant plus tangent minus sine is equal to x squared over x squared plus 1 to the 3/2 power. So instead, in our last step, we need to back substitute. We need to get everything back in terms of x. I'm going to say put 2x in here, but in truth, it could be in terms of t or y or something else. It just kind of depends on what's there. So in order to do that, we are likely going to need to use a triangle. And that triangle is going to come from the relationship that x is equal to tangent of theta. And in fact, for the sake of clarity, I'm going to go ahead and bring this down just so we can see it. So if x is equal to the tangent of theta, that describes for us the wobbliest right triangle in the world, describes for us the right triangle relationship that opposite over adjacent is equal to x. Likewise, that implies that our hypotenuse will be the square root of 1 squared plus x squared. And that means that we now can find all of these individual trig relationships or trig ratios straight out of the picture. So in here, what do we have? We now have, let's use the colors just for one more time. We have ln of the absolute value of secant of theta. Well, looking at our picture here, it looks to me like secant of theta is equal to adjacent over hypotenuse, which is 1 over the square root of 1 plus x squared. Oh shoot, I just did cosine, didn't I? I can fix that. Secant of theta is equal to hypotenuse over adjacent. So secant is going to be the square root of x squared plus 1. Then we have plus tangent. Well, it literally tells us that x is equal to tangent, so we can just throw in an x right there. Finally, we have to subtract sine of theta. Well, looking over at our triangle for a bit, sine is going to be opposite over hypotenuse, so we'll have minus x over the square root of 1 minus x squared. All of that plus c. And this, my friends, this is the function whose derivative is this thing. We have successfully executed trig substitution and solved the problem. And in truth, I mean, just look at that expression. Like, I feel confident that even the most intuitive among us wasn't going to anticipate that particular function being the origin of that derivative up there. It's honestly mind-blowing to me. Like, this is an exciting thing for me. I feel pride in finishing this. Actually, I don't feel pride just yet. Let me confirm that I did it correctly. I feel pride in finishing this because this is a lot. There's a lot going on here. But you can see it's actually more systematic than you might think. It really is a process. Choose your substitution, just replace everything with it, transform it into a trig integral, something that we can hopefully solve in an expedient way. You know, do whatever trig magic you have to do to get through there, and then anti-differentiate and back sub, and you are through. That completes the problem for us. And that's exactly what happened here. We actually have just evaluated this using trig substitution. I find it cool. Your mileage may vary, but at this point, there's no one here to argue with me. So I'm going to say that unequivocally, it is cool. Unequivocally, it's cool. It's a better way to say it. So having said that, I've done one. I'd really like to do one other problem just to make sure that we've kind of seen a little bit of everything there. I don't like to leave you with just like one example, and technically we did an example here, but it was before we knew about trig substitution. So let's go ahead and just do one more, and then we'll call it a day. So our final one that we're going to hit, and I'm going to bring over our little plan here and put it in the corner. Our final integral we want to evaluate is 32x cubed square root of 1 minus 4x squared. Whew! Whew! There's a lot going on here. So there is a lot happening. So we've got some stuff that we want to actually hit. And I will point out even before we begin here, and in fact this might be a little cheap here, but before we begin, something that will be really helpful to us is already just be thinking about like preparing for the structure we have. If we have 4x squared in there inside our integral, then we're going to have 2x squared being literally squared inside there. So we'll just make that, I just want to make that clear before we start that that's something that's happening. So to kick things off here, before we start to evaluate, as it says, first thing we need to check is, do we really need trig substitution here? So again, the most common way to check that and kind of verify that there's not an easier pathway is to look at the inside of any sort of radically structure and see if its derivative is on the outside. Unfortunately, the derivative of 1 minus 4x squared has a single x in it, not 3 of them. So this one is not set up that way. As I mentioned in the last one, there may be the possibility of some really like interesting and intricate integration by parts in there. But again, this is made for trig substitution, so we're going to take a shot at it. So we decided, yeah, we're stuck with it. So next we need to choose our substitution. And this one could be a little bit tough. So keep in mind, we normally, when we make a substitution, if we see like 1 plus x squared, we let x equal tangent and we make our substitution here. Here we do have 1 minus something squared, so it's screaming to us that we're going to use sine. And in fact, it's very tempting. I think most students would be tempted to let just straight up x be equal to sine of theta. The problem with that choice, though, is that we haven't taken into account the 2. We do need to deal with the 2 that's sitting there. So instead, I'm just going to like kind of take care of it in one shot. I'm going to let 2x equal sine of theta. Like that should take care of the process for us as well. If we replace this whole 2x with sine of theta, we'll have 1 minus sine squared, which is Pythagorean in all the right ways. So we'll start there. And that will, of course, affect our dx. In this case, we're going to have 2 dx on the left side equal to cosine of theta d theta. So you can tell we can't quite substitute in exactly the same way we would before. We'd have to do a little bit of finagling, but at the same time, we've gotten where we need to. So we now have a process to follow. I'm going to go ahead and just do one little move here. I want to be able to directly substitute. So I'm going to change this so dx is equal to 1/2 the cosine of theta d theta. Okay, having said that, let's make our substitution and see where things go. By the way, if you're checking off at home, there's where we're at so far. It's time for us to substitute in. So in our integral, we do have this 32. We then have x to the third power. And in here, once again, we can't quite do x straight in. So let's divide by 2 or multiply by 1/2 on both sides. We'll be able to replace this with 1/2 sine of theta all to the third power. And then we'll have our square root, which is going to be 1 minus 2x squared. And as we said, 2x is equal to sine of theta. So we'll get what we need there. And finally, our dx, as we saw in the previous one, is 1/2 cosine of theta d theta. And you can kind of see here that really in this problem, it's sort of just challenging to track everything and to make sure we have everything in place where we want it to. There's lots of little 2's that are kind of flying through here. So I'd probably say that this is like one step above the level I'd want to assess you on a timed exam. But at the same time, this is a really rich problem for us to be attacking. So having made this move, let's see if we can clean this up a little bit, see if we can prepare for the final steps here. So I see the 32 out in front. 1/2 to the third is going to be 1/8. Then we do have sine to the third of theta. Inside our square root, we have 1 minus sine squared, which we should know at this point is cosine squared. So we're going to have the square root of cosine squared of theta. And then as it says, we have 1/2 and a cosine lying around at the end with d theta. So finally, moving some pieces together and cleaning some stuff up, 32 over 8 times 2, that's 32 over 8 is 4, divided by 2 is 2. The square root of cosine squared is cosine. And after all of these moves, it looks like we're going to have, out in front, we're going to have a 2 sine cubed of theta. And then we've got cosine and cosine, so cosine squared of theta, all d theta. So we've made our substitution. We now have our full trig integral. That's great. Good job, us. The calculus is on pause now. Now it's time for us to pull out whatever trig identity is necessary to transform this guy. So what do I see? So in looking in here, this is just kind of my thought. I haven't looked down at the things here. There's been no jump cuts either. As I look at this, I see sine cubed. And my thought is that extra 3 means that we have an odd number of signs. So this is just me. My instinct here, and it could be wrong. I absolutely could be wrong. I'm just trying to be as authentic as I can here. My instinct is what we should do is we should change this into sine squared by pulling out a single factor of sine of theta. My thought process then, again, as I said, could be wrong. My thought is we could then transform everything in here into cosines by using a Pythagorean identity. So let me just take a quick look and see if this is in fact a good strategy. Is it? Yes, it is indeed the correct strategy. So let's do it. So we want to evaluate this. I'm going to pull that 2 out in front just for clarity. In addition, I want to replace sine squared with 1 minus cosine squared of theta. We'll then have a cosine squared of theta left over and a sine of theta d theta. So there is our integral. We've now transformed it into one that we can evaluate because notice this is ready for classic u substitution. And we haven't gotten to use u substitution actually on this page, so we'll just do it off to the side. We can use the letter u. I'm going to let u equal cosine of theta. That means du is going to be negative sine of theta d theta. It's almost comforting to be back in the old world of u substitution. And if we make some substitutions, move some stuff around, I guess I'll do this the old-fashioned way. We'll get d theta is du over negative sine of theta. If we go into our integral and make those substitutions to kind of get things popping, we're going to have 2 times the integral of 1 minus u squared. I'll drop the color here in a little bit because I know it takes a little bit longer. 1 minus u squared times u squared, and then times sine of theta times d theta, which we just said was going to be equal to du over negative sine of theta. And with that in place, notice we've got some stuff to clean up. The sine of theta's divide out. That negative sign can move out in front. We can also distribute the u squareds in pretty easily. This is going to give us negative 2 times the integral of u squared minus u to the 4th du. And you know what? With that negative sign in there, I'm going to go ahead and just distribute that negative sign in, honestly. This is just a personal choice. You probably wouldn't do this normally, but I just want to clean this up as much as I can. This will be 2u to the 4th minus u squared du. And with that, we're in position to finish this off. So let's do this, at least the trig integral portion. I can't lie about the other one. This is going to be 2 times, it looks like 1/5 u to the 5th minus 1/3 u to the 3rd. And then, of course, we'd have a plus c here. We're just going to, I'll put that in there. Now, in here, I could choose to back substitute, or I could choose to factor, and I think I really do want to in this case. This is one of those situations where, again, your answer might end up looking different than mine. But there is a good factoring method that's out here. We could find a common denominator. Is that what I did last time? I did. I'm going to go ahead and do it. I think that it's fair to do that. So in here, what I'm going to do is I'm going to multiply up and down by 15. So this is kind of a classy first step. Multiply up and down by 15. That'll give us a 3. Oh, and you know what? I'm also going to factor out a GCF of u to the 3rd. Did I do that right? U to the 5th. Ah, geez, I wrote a wrong value in there. Fixed. Okay, it's because I haven't eaten. It's getting to me. So, that was fine. Okay, so we got 2 15s u to the 3rd factored out in front. We're going to be left with 3u squared on the inside minus 5, all plus c still. And then finally, we can back substitute in here for u. So in here, what will we get? We'll have 2/15. I'm going to leave it in parentheses this time, so u cubed. So that's going to be cosine of theta cubed. And then our other factor is going to be 3 times cosine squared. Oh, finally. And see, just like changing colors is somewhat taxing. All plus c. Okay, so at this point, we have our full trig antiderivative in there. We now need to actually evaluate this integral by back substituting. So we're going to pull out the orange for a second. We're going to draw in our triangle here and hope for the best. So with our triangle, as we said at the beginning, we said let 2x be equal to sine of theta. So in here, if that's theta, sine of theta would be 2x over 1. The third side would be 1 minus 2x squared, otherwise known as the square root of 1 minus 4x squared, because we'd have the whole 2x squared. Given that information, the important thing to take out of that triangle is that the cosine of theta is equal to the square root of 1 minus 4x squared, over 1, obviously, so it's all fine. And given that information, we can now go substitute it into our antiderivative. So making that move, we're going to have 2/15. We're going to have the square root of 1 minus 4x squared, all cubed. And then in here, since we're squaring it, this is kind of nice, we're going to have 3 times this thing squared. So 1 minus 4x squared, and then all minus 5, and then finally plus c. So this is the answer that I imagine most of you would want to stop at, simply because like everything that follows is just algebra. But in truth, I'm going to break my own rule for a second here. And I'm going to shrink everything so that way I have a chance to actually fit this in. I'd like to at least show you what what I would call the best version of this answer would look like. You may disagree, but I feel pretty confident that it's better. So in here, if we wanted to simplify this just a little bit, kind of pulling things together, we'd have the 2/15. This is 1 minus 4x squared to the 1/2 power, so we could rewrite that as 1 minus 4x squared to the 3/2. And then inside here, this is going to be 3 times 1 minus 4x squared minus 5. That's what's inside that factor, which if we distribute it out, we're going to have 3 minus 12x squared minus 5, which is going to be, let's see, it looks like negative 2 minus 12x squared. Can that really be correct? Is that right? Wow, it is. Okay, go figure. So if I want to clean this factor up a little bit too, that's going to be negative 2 times 6x squared plus 1. So if I want to rewrite this factor, I've got now negative 2 quantity 6x squared plus 1, all plus c. But finishing this all off, geez, I don't really have a space. I'll do it right up here. Finishing it all off, we can pull that negative 2 out in front. We'll have negative 4 over 15. You can see why not simplifying might actually be a good strategy here, by the way. To the 3/2 times 6x squared plus 1, all plus c. And that is our final answer. So did I choose one that was just like horrific in the final steps to finish this lesson off? Yeah, okay, I did. But having said that, this is a nice, rich problem. And as I said, some of these problems are great ones to do, but not necessarily ones that would fit into an exam. But that doesn't mean they're not valuable to be able to attack to develop this technique, this new strategy we have. Having said that, though, that does complete what I'm going to be presenting in this lesson. This finishes up what's there, which is good because it's quite long. But that's normally what happens with this particular lesson. So just to kind of reiterate what's here, when we kick things off, we talked just about substitution in general to remind us of sort of the idea behind it. And we pointed out that substitution can be fairly arbitrary. Like, we really have the ability to transform any integral into another form that has the same value, just using a sort of different variable system. After that, we showed you the idea that some of these structures, including this one involving a semicircle, actually require a technique called trig substitution, and we sort of motivated it with the Pythagorean identity. And then I just kind of demonstrated it for you and showed you what it actually looks like before talking about the substitutions themselves, which do match what we saw earlier with inverse trig integrals. After that, we did some simple substitutions to transform integrals into trig integrals. We didn't evaluate them because, you don't want to evaluate some of these. And then afterwards, we did two problems, working through the process and talking you through the strategy here which is admittedly pretty involved. This is a major challenge. I'm not going to lie to you, it is. But at the same time, it's a rewarding one. Like a success on a trig substitution problem is an opportunity to really prove that you're comfortable with trigonometry, with antidifferentiation, with identities, like all sorts of things all kind of come up in here, with substitutions of all kind, with triangles. There's just lots of really rich stuff happening. So, as I mentioned earlier, this is one of my favorite lessons. I don't need to stick fun with trig substitution in the title because I really do take pride in it and enjoy the process. So having said that, in the video itself, if there were more time, we'd probably take a moment just to go through this integral, which is equal to arctangent of x, by the way, and show you how trig substitution can actually sort of nerf this problem. It says just for kicks. Like, I encourage you to give this a shot and just try out something like one of the basic inverse trig integrals and see if trig substitution maybe does the trick for you. Maybe it'll make things a little bit faster. And then, as I mentioned, I also have an extra example in here, which is often the first example I do. I chose not to do it that way just for the sake of time and space. Other than that, oh yeah, there's that photo from the first time I taught trig substitution. I think if memory serves, I threw a bag of chips and said, if anyone wants it, you can have it. And Tony dove on the carpet and like got rug burns doing it. Beside the point. The important thing here to note is that does complete the lesson on trig substitution, a lesson that was lost into 2020 like so many other things. And honestly, you should probably be okay with that if you're in my class this quarter, because this would have just kind of would have cost us the gobble turkey activity, if I'm being honest with you. So I think that's okay, but at the same time, I wanted to make sure that I at least presented it and had it available for you in case you wanted to learn it at some time soon, and also so that I have the resource in the future, since I had a few minutes today after the final. So, as always, thank you for watching the video. I hope it's been helpful to you. Obviously, I take things a little slow, but I know most of you have figured out the whole idea of like 1.5 timesing it when I'm doing a lecture this way. So I won't be able to tell that you do it that way, so that's all fine. Hope you have a great night. If you're watching this from my class in 2020, enjoy your winter break and enjoy the rest from finals. You deserve it. And as always, talk to you soon.